Model quantization represents weights, and sometimes activations or caches, with lower numerical precision. A model originally stored with 32-bit or 16-bit floating point values may be converted, so many weights use 8, 6, 5, 4, or fewer bits. The runtime combines those compact values with scales and other metadata to approximate the original computations during inference. Lower precision reduces the bytes that must be stored, loaded, and moved through memory. That can make a model fit in limited VRAM or system RAM and reduce memory bandwidth pressure during token generation. A model that remains fully on an accelerator may run much faster than a higher precision version split between GPU and CPU. Smaller files also download and load more quickly. The trade-off is approximation. Quantization can alter probabilities and model behavior, with effects that depend on architecture, method, bit level, and task. Some models tolerate moderate quantization well. Aggressive compression may damage reasoning, coding, instruction following, or rare knowledge. Hardware and runtimes also differ in which formats they accelerate efficiently. Quantization is not magic compression. It does not remove context cache memory, runtime overhead, tokenizer files, or every activation. It does not increase the model's underlying capability or guarantee speed. The useful question is whether a particular quantized artifact fits the target system, runs efficiently in the selected runtime, and preserves acceptable quality for the real workload. Local inference is frequently constrained by memory capacity and bandwidth. A full precision language model may exceed the VRAM of a consumer GPU or the system RAM of a small computer. Quantization reduces the weight footprint, allowing a larger parameter count or more operating headroom on the same hardware. That headroom matters because the runtime, context cache, operating system, and other applications also need memory. Fit changes performance. When a quantized model remains entirely on the GPU, generation can avoid repeated transfers to slower system memory. On CPU-only systems, smaller weights reduce RAM demand and the amount of data moved through memory channels. Loading and startup can improve because fewer bytes are read from storage. These benefits vary with hardware and runtime. Compact values still have to be unpacked and processed efficiently. Quantization expands practical choice, but it does not make every large model sensible. A heavily compressed model may fit while responding slowly, leaving little context headroom, or losing too much task quality. A smaller model at a healthier precision may be faster and more accurate for a specific job. Capability depends on model design and training, not parameter count alone. Think in terms of a complete resource budget: weights, context, cache, batch, runtime, and concurrent work. Select a quantization that fits with margin and test it on real prompts. The purpose is not to squeeze the largest possible file through startup. It is to make useful local AI responsive, stable, and affordable on available hardware. FP32 uses 32-bit floating point values and has been a common training and reference precision. FP16 uses half as many bits, reducing memory and taking advantage of supported accelerator operations. BF16 also uses 16 bits, but allocates them differently, preserving a broad numerical range that is useful in training and some inference workflows. Hardware support determines whether a precision provides an actual speed benefit. INT8 represents quantized values with 8-bit integers, often with per tensor, per channel, or group scale information. 4-bit and lower bit weight formats reduce storage further, but the nominal bit count does not include every scale, lookup, alignment, or metadata cost. Actual file and loaded sizes are therefore larger than parameters multiplied by bits alone. Weights are the learned model parameters. Activations are intermediate values produced while the model processes input. A system may store weights at low precision while computing activations or selected layers at higher precision to preserve quality. The key value cache has its own format and memory cost, which grows with context length and active sequences. Precision affects more than size. It changes numerical resolution, supported kernels, memory traffic, and sometimes output behavior. Lower is not automatically faster if the hardware or runtime lacks an efficient implementation. Treat labels such as 4-bit as a starting description, then inspect the quantization method, runtime support, measured memory, speed, and task quality. GGUF is a model container commonly used by llama.cpp and compatible local runtimes. It can package quantized tensors together with model architecture information and other metadata needed for loading. A single model family may be published as many GGUF files, each using a different quantization method or size. The file name is useful, but runtime support and embedded metadata determine whether it can be loaded correctly. SAFA tensors is a safe, efficient tensor storage format widely used in model repositories and framework workflows. SAFA tensors files may contain full precision, half precision, or quantized tensors depending on the model and loader. The extension alone does not tell you the numerical precision, and it does not guarantee that a local runtime supports the model architecture or quantization scheme. Models often require more than weight files. Tokenizer vocabulary, tokenizer configuration, special token definitions, generation settings, prompt templates, and architecture configuration influence how text becomes tokens and how conversations are formatted. Mixing weights with an incompatible tokenizer or template can produce poor output even when the model loads successfully. Before downloading a variant, identify the intended runtime, architecture support, quantization method, context requirements, and available memory. Confirm provenance and license terms. The same base model can appear in multiple containers and many quantized variants because different hardware, runtimes, and quality targets need different trade-offs. Format is part of the compatibility chain, not a universal indicator of quality. Local quantized model names often include labels such as Q2, Q3, Q4, Q5, Q6, or Q8. At a high level, the number indicates the approximate weight precision family. Lower levels use less memory and usually accept more approximation, while higher levels retain more information and require more space. Suffixes identify specific methods, group sizes, or mixed precision choices and are meaningful only in the context of that format and runtime. Q4 variants are often a practical starting point because they provide substantial memory savings while preserving useful quality for many models and tasks. That is a heuristic, not a guarantee. A particular architecture may respond differently, two Q4 methods may not behave identically, and a coding or reasoning task may reveal losses that casual conversation does not. Q2 and Q3 can make otherwise inaccessible models fit, but aggressive compression increases quality risk. Q5 and Q6 consume more memory and may preserve behavior more closely. Q8 often approaches the memory cost of higher precision while remaining useful when quality is prioritized and hardware has room. Speed does not increase monotonically as bits decrease. Kernel efficiency, offload, memory fit, and hardware support all matter. Choose candidates around the hardware boundary. If Q5 fits with context headroom, compare it with Q4 rather than assuming the smaller one wins. If only Q3 fits fully on the GPU, compare its quality and speed with a smaller model at Q4 or Q5. Quantization level is one decision among model family, parameter count, context, runtime, and workload. Begin with the complete memory budget. The quantized weights must fit alongside runtime buffers and the key value cache. The cache grows with context length, active sequences, and model architecture. Batch settings add temporary pressure. Leave headroom instead of selecting a file whose size nearly equals available VRAM. Full GPU offload is often fastest when supported and memory allows. Partial offload places some layers on the GPU and leaves the rest on the CPU, which can enable a larger model, but increase transfer and CPU work. CPU-only inference remains practical for smaller quantized models when system RAM and memory bandwidth are sufficient. Unified memory systems share capacity between CPU and GPU, so the model competes with the operating system and other applications. Context can change a successful startup into an allocation failure. Test the configured maximum as well as a normal prompt. Measure time to first token, prompt processing speed, generation speed, VRAM, RAM, and stability. A model that barely fits may run slowly, prevent other applications from using the GPU, or fail when a long document arrives. Optimize for the actual service envelope. A smaller or slightly more compressed model that remains fully accelerated with context headroom may outperform a higher precision version that spills into system memory. Conversely, if both fit comfortably, higher precision may offer better quality with little operational cost. Hardware fit determines which comparison is meaningful. Measurements determine which option wins. Quantization changes the approximations used during inference, so quality loss may be subtle rather than a complete failure. A response can remain fluent while becoming less precise, more repetitive, or more likely to miss a constraint. Hallucination is influenced by the base model, prompt, data, and sampling as well as precision. Quantization does not create or remove it in isolation, but aggressive compression can reduce reliability. Reasoning tasks may reveal mistakes in intermediate steps or consistency. Coding tasks can expose errors through compilation, tests, API use, or adherence to requirements. Instruction following should be evaluated with prompts containing several constraints. Long context tests should check whether the model retrieves details from early and late portions rather than merely producing plausible prose. Quality sensitivity is workload specific. A conversational assistant may tolerate a compact quantization that is unacceptable for structured extraction, technical analysis, or domain terminology. Different model architectures and quantization methods can react differently at the same nominal bit level. A strong smaller model may outperform a larger aggressively compressed model. Evaluate outputs with clear criteria: factual correctness, task completion, format compliance, consistency, and useful uncertainty. Use deterministic or controlled settings where possible and repeat prompts because sampling introduces variation. Do not assume that a popular quant level is good enough, and do not assume every difference is caused by quantization. Compare against a higher precision reference and the real acceptance threshold for the task. Build a small evaluation set from the intended workload. Include common prompts, difficult edge cases, required formats, representative context lengths, and tasks with verifiable outcomes. Keep the base model, runtime, prompt template, sampling settings, and hardware constant while comparing quantization variants. Otherwise, the test cannot isolate precision as the changed variable. Compare at least one compact candidate, one practical middle candidate, and a higher precision reference when hardware allows. Measure file size, loaded VRAM or RAM, model load time, time to first token, prompt processing speed, generation speed, power or temperature if relevant, and errors. Run multiple trials so warm caches and random output do not determine the result. Score quality against predefined criteria. For coding, run tests. For extraction, compare fields. For structured output, validate the format. For analysis, review correctness and consistency. Long context evaluation should use material that requires retrieval from different positions. Record failures, not only average impressions, because one serious instruction following defect may outweigh a small speed gain. Keep a concise decision log with model revision, quantization file, runtime version, settings, hardware, measurements, and acceptance result. Select the lowest resource option that meets quality and reliability requirements with memory headroom. Revisit the decision when the model, runtime, hardware, or workload changes. Testing turns quantization from a label into an evidence-based deployment choice. Quantization lowers the numerical precision used for model weights and sometimes other data. It reduces memory and bandwidth pressure, making local inference practical on hardware that cannot support the original precision. The savings can improve model loading and allow more layers to remain on an accelerator, but scales, metadata, activations, runtime buffers, and context cache still consume memory. Precision labels describe trade-offs, not guaranteed outcomes. FP16, BF16, int8, and low-bit formats require compatible hardware and runtimes. GGUF and SAFA tensors are containers used in different workflows. Neither extension alone establishes quality or precision. Tokenizers, templates, architecture metadata, and model revisions must remain compatible. Q4 is often a useful baseline, while lower levels favor fit and higher levels favor fidelity. The right choice depends on model architecture, available VRAM or RAM context, batch, offload, kernel support, and task sensitivity. A model that barely fits may run worse than a smaller or more compact option with headroom. Choose through testing. Compare several variants with the same runtime, prompts, settings, and hardware. Measure speed and memory, evaluate factual and task quality, repeat trials, and record the configuration. Quantization succeeds when it preserves the quality required by the workload while delivering stable, maintainable performance on the target system.